Section 1.2.1 Compute, VMs, Containers, Serverless, Conceptual Understanding. When we say compute in the cloud, what we really mean is the environment where your code executes. Everything at some point needs CPU cycles. Websites, APIs, mobile backends, data pipelines, authentication services, they all need compute. The cloud offers three dominant ways to run it: virtual machines, containers, and serverless functions. These are not competing technologies. They are different engineering choices for different contexts. And in real systems, you almost never use just one. You combine them. Let's start with the most traditional model, because it closely resembles how computing worked long before the cloud. A virtual machine behaves like a real computer. It runs on top of a hypervisor, which is software that creates and manages virtual machines by sharing physical hardware among them. Conceptually, it's like slicing one powerful physical server into multiple isolated servers, each behaving as if it were its own machine. Inside a virtual machine, you install an operating system, configure services, and secure it just like you would on physical hardware. The cloud provider handles the underlying infrastructure, racks, power, cooling, and networking, while you are responsible for everything inside the VM. That includes operating system updates, firewall rules, monitoring, and scaling. This fits directly into the shared responsibility model we discussed earlier. Virtual machines offer full isolation and full control over the operating system. They make it easy to lift and shift existing applications into the cloud with minimal changes. The trade-offs are also clear. Virtual machines start slowly, often taking minutes. They have higher overhead because each VM runs its own operating system, and scaling is usually more manual. This model is still extremely valuable when workloads were originally designed to run on a server, or when strict isolation and compliance are required. In practice, companies like Airbnb use Amazon EC2 to host back-end services, scaling vertically with larger instances or horizontally with more instances during peak traffic. Banks often rely on Azure VMS because of strong Windows Server support and database isolation. Machine learning engineers frequently use preemptible VMS to train models at lower cost while tolerating interruptions. Over time, engineers started looking for a more efficient way to run applications without paying the cost of a full operating system for every workload. That's where containers enter the picture. Containers don't simulate hardware. Instead, they share the host operating system and isolate applications using kernel features such as namespaces for process isolation and C groups for resource limits. The key idea is simple. Instead of packaging an entire operating system, you package only the application and its dependencies. Because of this, containers are dramatically lighter than virtual machines. Starting a virtual machine usually takes minutes, while starting a container takes seconds. This makes it possible to run many more workloads on the same hardware, increasing density and improving resource utilization. Containers are deployed predictably because everything an application needs is bundled together, usually as an image built with tools like Docker. This consistency makes it much easier to move workloads from development to testing and into production. The benefits are speed, portability, and consistency across environments. The trade-offs still exist. Containers share the host kernel, which means isolation must be configured carefully to avoid security issues. At scale, you also need orchestration to manage deployment, failures, and traffic. This is where systems like Kubernetes come in, handling restarts, rescheduling, load balancing, and rolling updates. Managed options such as Amazon ECS or Google Kubernetes Engine simplify this further. In real systems, containers became the foundation of microservice architectures. Shopify deploys services like authentication, order processing, and payments in separate containers so each can scale independently. Uber runs thousands of containerized services orchestrated by Kubernetes, relying on replicas and auto-healing to maintain availability. Capital One dramatically reduced provisioning times by moving from VM-heavy workflows to container-based platforms. As teams continued to abstract infrastructure away, a natural next step appeared. What if you didn't manage servers or containers at all? This is the idea behind serverless computing. With serverless, you don't manage machines or runtimes. You write code and deploy it as functions, and the cloud runs those functions only when they are triggered. This model is often referred to as function as a service. The defining characteristics are straightforward. There is no idle cost because nothing runs unless it is needed. Scaling happens automatically, often to thousands of concurrent executions. The mental model is similar to electricity. You pay only when it is used, with no always-on bill. This aligns perfectly with the OpEx model we discussed earlier. Serverless offers major advantages for certain workloads. Operational overhead is minimal, scaling is automatic, and costs are efficient for sporadic or unpredictable traffic. The trade-offs include cold starts, stateless execution by default, and limits imposed by the provider. Serverless is particularly well suited for event-driven systems. This includes data processing triggers, IoT signals, analytics bursts, notification services, and lightweight APIs. Platforms like AWS Lambda, Azure Functions, and Google Cloud Functions are widely used for these cases. Coca-Cola processes vending machine telemetry with serverless functions that scale from zero to massive workloads. Chatbots in Microsoft Teams rely on serverless to handle sudden spikes. Spotify uses serverless components to personalize playlists, integrating them with messaging and analytics systems. At a more advanced level, it's important to understand that serverless functions are ephemeral. They do not store state locally. Any state must live in external services such as databases, caches, or object storage. Recently, serverless has expanded into hybrid models, including services that run containers without managing clusters and edge platforms that execute code closer to users for low-latency applications. With all three models in mind, the real question becomes how engineers actually choose between them. In practice, virtual machines, containers, and serverless functions coexist within the same system. Virtual machines provide strong isolation and are often used for legacy or regulated workloads. Containers offer efficiency and portability and are ideal for microservices and rapid development. Serverless emphasizes simplicity and elasticity and works best for bursty, event-driven workloads. Many production systems mix all three approaches. Netflix uses virtual machines for strong isolation, container fleets for scalable services, and serverless functions for automation. A realistic e-commerce platform might use containers for APIs, serverless functions for payment notifications, and virtual machines for specialized databases. There is no universally correct choice. There is only what is appropriate for a specific requirement. Cost, security, compliance, and traffic patterns all influence the decision. Virtual machines make sense for steady workloads. Containers excel when density and speed matter, and serverless shines when eliminating idle capacity is critical. This way of thinking is what stands out in interviews, because it shows judgment rather than memorization. Compute is only one part of the picture. Storage provides memory, networking enables communication, and security protects both flow and state. Now that execution is clear, we can move on to where application state safely lives. End of section 1.2.1. Compute.